fine now?
I can, yeah,
Yeah.
I can see it now.
Okay. Yeah. So now what I have done, I have taken a simple model. I have taken a cube. Okay. So I'm just opening my model. So once you open Ansys Workbench, you would be seeing here different types of analysis systems. Okay. So we were discussing about finding out the domain or physics or the preliminary decision. We were talking about what type of analysis I have to do. So depending, as I said, depending upon the output you are looking for, you have to select the appropriate analysis system. So if I'm looking for a stresses or deformation, I would be selecting static structural. If I want to know what are the natural frequencies, I will select modal analysis. If I want to know thermal effects, I will be selecting a steady state thermal analysis. Okay. So now what I have done, I have this cube. Okay. So I have taken this one cube. Okay. So you can see the geometry. So this is my cube. This is 30 by 30 by 30 dimensions I have taken. Okay. Now, whenever you are solving any problem in your in Ansys workbench, by default it will take structural steel as a default material. Okay. So here, just clicking on the materials, you can see what are the material properties of the material you have assigned to your geometry. Okay. So you can see all these material properties which are by default available into Ansys Workbench material library. Okay. Next is meshing. Okay. So dividing your structure into number of elements. So here you can see this particular cube is being divided into number of elements. Okay. Now, for analysis setting, so what I have to do, right click and I will have to insert the analysis setting. So what I have done, this bottom thing, I have fixed this. This surface I have fixed, and from upward, I have applied a force. Okay, so this force I have applied of 200 kilonewton of downward force or a compressive force I have applied. Okay. Now what I will do, I will just solve this and I get the equivalent stress as 449.6 I am getting. Now, what is the uh, what is the yield stress of structural steel or a steel? It is around 250 MPa, but what I am getting a stress is 449.6 MPa. Means somehow my solution is not accurate or it is an inaccurate, right? So why this happened? Because I have added linear material properties of structural steel. Okay. Now, if you go back and I will open the engineering data. Engineering data is a material library available in Ansys Workbench. Okay. So if I go to engineering data sources, you can find out here different material libraries. Okay. You can see here general materials, additive, geomechanics, general nonlinear materials are also there. Okay. So now what I am doing in the next step, I am just assigning, I am picking a nonlinear material property of the structural steel. Okay. So here you can see the bilinear representation of your structural steel is being given. Okay. So nonlinear graph. So there are two ways of representing the nonlinearity of material. One is a bilinear and another one is a multilinear. So whenever you are doing a applying a bilinear properties, you need a yield strength and you need a tangent modulus of your material. Okay, and multilinear is nothing but a number of stresses and strains you have got from the experimental results. Okay, those properties you have to put to represent the curved path or a non-linear uh, linear curve of your material. Okay, so in this particular, now I'm say getting a same geometry, but I have added a non-linear material property to it. Now let us say what happens. Yeah, now you can see for this same geometry, I have assigned a structural steel NL. It means structural steel non-linear. I have applied a non-linear material property to this structure. Rest all things like a fixed support at the bottom and the same amount of force I am applying at the top of my tube. Okay. Now, if I solve this model, what happens? I am getting the different stress value. I am getting the equivalent maximum stress as 298.18, which is more close to 250 MPa, which is the yield strength of the structural steel. So what we learned from here is, from this particular problem is that how the non-linearities into the material takes place. Okay. So if your model, if the things, whatever you are applying the initial conditions, application of materials, or due to that load, some amount of load, your material is experiencing the non-linearity into your into it. So that's why you are not getting the appropriate results. But if once I apply a nonlinear material properties, what happens? My solution changes. Okay, and I get a more accurate solution over here. Fine. So apart from these three non-linearities, there are different another non-linear applications also there. Like there are whenever you are doing FEA, there are implicit approach and the explicit approach. Okay, so there are various non-linearity applications include like a metal forming process or crash and impact analysis, or it may be a different manufacturing process analysis, where the non-linearity into the structures happens. Then it would be non-linear materials, as I said earlier, elastomers, polymers, right? We discuss about different hyperelastic materials. Then there are analysis of system which are subjected to ultimate loads like plastic behavior or shakedown response. Chabichi material model is there where uh, shakedown happens over there, or there would be different forensic evaluations. So wide break and all. So these all things include the non-linearity into the structures, and those particular problems should be solved with a non-linear approach. Then another way of solving the structural analysis is a dynamic approach. Okay, so there are various so this static structural analysis neglects the effects of the structure's inertia on the solution. Okay, so inertial loads are not uh, considered whenever you are doing a static structural analysis. So from practical perspective, uh, what happens is that this means that the loading is being applied slowly through enough, and the structure is responding slowly enough so that the acceleration forces are negligible compared to the elastic forces. So there are various examples where dynamic analysis is required, right? Like a vibration problems or impact or a crash problems. So I will showcase you one more demo on the vibrations, because we are studying this almost in our engineering curriculum. Okay. So in dynamics, that is into vibrations, we are dividing it into free vibrations and the forced vibrations, right? So what free vibration does? Free vibration gives you the natural frequencies of your structures, and there are various force vibrations as well. So in simulation, the free vibration analysis is being done with a modal analysis. Okay. Similarly, there are various forced vibrations like a harmonic response. So you have a harmonic response over there. So whenever harmonic loads, that is a sinusoidal loads, are being applied on a structure, then we do a harmonic analysis over there. Then you have a random vibration or response spectrum analysis, or there would be a transient structural analysis. So all these forced vibration analysis can also be done with help of simulation. Okay, so I will be here now showing you one demo onto the modal analysis, that is how we calculate find out the free vibration or the natural frequency of a structure. So what I have done is, from analysis system I have picked the modal branch. Okay, because now I want to know what would be the natural frequency of the structure. So what I'm doing, I'm taking a simple
Yes,
structure. I have
parody,
already
toted like a
created a
prodigy, cause they
geometry.
find me hard to
So
beat. They call me
I'm taking a plate with hole. Okay. So I will just open this model branch. So it's just opening. So modal analysis is nothing but finding out the natural frequencies of the structure. Okay. So whenever you are doing a modal analysis, so like structural analysis, what we did is we applied few loads and the boundary conditions to it. Now we will see how to solve any modal analysis problem, and how the settings are to be applied. Okay, so now you can see here, this is one plate, and I have put some hole into this plate. Okay, so now it is the same like geometry. You can see this plate with hole. Now here into the geometry, you can see here the different characteristics of your geometry. Okay, or your structure. You can see here stiffness behavior is flexible. Then you can see the material assignment. Okay, so as for this, by default it will assign the structural state. But if you want to take the another material, let us say I want this particular geometry should be of aluminium. Okay. So what I have to do, I have to go to engineering data. Okay. Now you have to go to engineering data sources. Fine. You have to select a library out of it. So I will select a general material library, and from this I will pick aluminium alloy. So what you have to do, you have to select this, and beside that plus sign is there. So I have to just select this plus sign. I have to just go back to the project, and here you can see the refresh button. Okay. So just I refresh the project. Okay. So all this is the updating is going on. I have just refreshed it. If I come back to my project, I can see here, you can see structural steel and aluminum alloy. Okay. So here you can come back and assign aluminum alloy as a material to your geometry. Okay. Now you have seen, you can see the material properties of aluminum here. You can recheck it over here, and you can go back to engineering data if you want to modify something. Okay. Now here in meshing, I can just right click and generate mesh. So automatically the software will generate mesh over here. And let us say if you further go and change the material, so meshing of this particular geometry, then in the meshing there are various options. Okay, you can see here, you can just change it. You can see different element orders. You can see physics preference is mechanical, since you are working onto the mechanical. Let us say if you are working on a non-linear mechanical, then you have to select the non-linear. But whenever you are doing any dynamic analysis problem, you are any type of non-linearity, maybe it is a material contact or geometric non-linearities, those are not considered whenever you are doing a free vibration analysis or any of the dynamic analysis except transient structural analysis. Okay. Then you can change the sizing. Okay. As of now, it has taken the default and you can change the size of it. You can see the span, angle, center is coarse. I can make it fine. Okay. You can change various changes into it. You can, by default, it is a size it is given. So I can just give a 5 mm size to my each element. And again, I can generate the mesh. Okay. So now this is your updated mesh. I have changed it. I have given the 5 mm size to my element. You can still go ahead and you can still change the meshing. I can just give 1 mm size to my meshes. Okay. And I can just generate the mesh again. So you can change the mesh. Okay. There are various settings to be done while doing the meshing of your structure. Okay. I'm just showing few of this. I have made it very fine 1 mm. So it will be taking some time. You see. So this is a very fine mesh we have generated now. Okay. Because we have taken just 1 mm size of the mesh. Fine. Then now for model analysis, you have to do now few analysis settings. Okay. So whenever you are doing a model analysis, you can see, right click, you can see only the supports, and you can see some loads like inertia, rotational velocity or thermal conditions you can apply. But whenever you are doing a free vibration analysis, you are not applying any external loads to it. Okay. You are not applying any force or pressure or anything. Okay. So now I will just apply some boundary conditions. So I will apply a fixed support. Let us say this edge of my plate is fixed. Okay. I just applied a fixed support. Now I will go to analysis setting. So by default, software will extract 6 mode shapes, but you can have a number of mode shapes. So I am asking for 10 mode shapes now to the software. Okay. So it will extract now 10 mode shapes. Then right click and solve. Since we have done a very fine mesh, it is taking some time because you have learned that it will first solve on the element level and then it will integrate all those elements together. Okay. So now it is calculating on each of the element, and later uh, it will be just integrating it. See here at the bottom the progress, how it is progressing. So you can see here you have got the frequencies. So the first frequency, whatever the first frequency you get, it is called as a fundamental natural frequency. So 416.16 hertz is your fundamental natural frequency, and you can see the another preceding 10 mode shapes of it. Okay. Now if I want to see, these are the 10 first 10 natural frequencies you have got. Now if I want to see how it behaves, how the mode shapes are there, so I have to select this all, right click and create mode shape results, and I have to evaluate all the mode shapes. So now you can see this is my first mode shape. So this is how it behaves. Now you can see the second mode shapes. So this is how it behaves in a second, for second natural frequency. Then this one is a third. Then this is fourth. Then later on. So in general, you just keep in your mind the first 6 mode shapes, whatever you get, are called as a rigid body mode shapes. Okay. Since we have seen there are 6 degrees of freedom for your three-dimensional structure. Okay. So for this first 6 degrees of freedom, there are these first 6 mode shapes are called as a rigid body mode shapes, which are associated with your degrees of freedom. 7 onwards you get the another set of frequencies. Those are due to the flexible nature of your structure. Okay, so this is how the modal analysis is being done. Then there is a thermal analysis which can also be done. Okay, so we have seen, so if you are doing a thermal analysis, if you want to see the thermal effects, then we can do the thermal analysis. So the solution atoms of interest may include the temperatures, thermal gradients, heat flux, reaction heat flow, etc. So again, into this thermal analysis includes linear versus non-linear thermal analysis, and also steady state versus transient thermal analysis. Okay. So a linear thermal analysis assumes that the relation between the applied thermal loads and the and the temperature is linear. Similarly, like a structural linear and non-linear analysis. So your heat flow versus temperature is linear when it is a linear thermal analysis. So what are now the sources of non-linearity into the thermal analysis? Okay, so the nonlinearity into the thermal analysis occurs due to temperature dependent material properties. So there are various temperature dependent material properties due to which the material nonlinearity may happen into the thermal analysis. Also, there are various temperature dependent convection coefficients of there. So this also causes the nonlinearity in thermal analysis, and another reason is a radiation. Okay, so the nonlinear thermal problems have similar characteristics to the nonlinear structural problems. So for solutions involving a large temperature range, a nonlinear analysis should be considered. So what is so now we will be discussing upon the steady state thermal analysis versus the transient thermal analysis. So steady state thermal analysis computes the final temperature distribution in an interval during which the thermal load remains constant and it neglects the time dependency of a solution, wherein the transient thermal analysis is required when the loading is changing with time faster than the structure can respond thermally to this change, or when a detailed time history of the temperature solution is required. So what are the different examples where the transient thermal analysis is required to include is whenever we want to determine how long will it take for a pot of water to boil. So this is one occurrence, or this is one situation where you may have to include the transient thermal analysis, or you have to obtain a maximum and minimum thermal gradients in a engine component during a flight. So there are various readily solvable structural problems, like many linear and non-linear static analysis can be readily being solved. The typical features are the different loading like point loads, specified displacement, then relation between the displacements. So we call it as a constant equations. So you can put the relation between the displacement as a constant equations for a loading over here. You can apply pressures, you can apply accelerations, linear, maybe linear or a angular acceleration, or we can have a thermal loading. You can add various material properties, maybe a material is isotropic, orthotropic or anisotropic. Already we discussed you can simulate the composite materials as well, which is an example of orthotropic materials. Okay, so there are different material nonlinearities we have seen, that is nonlinear elastic material, isotropic plasticity, primary and secondary isotropic creep. So these are the various material nonlinearities which you can solve over here. And there are various geometric nonlinearity like stress stiffening, large deflections, large strains, gaps with or without frictions, nonlinear springs, cables, buckling. So here on the right, you can see the nonlinear static analysis, which is an example of the large deflection and contact analysis of the spring. So there are many linear and nonlinear dynamic analysis also which can be readily solved. So typical features of this analysis include a modal, that is a natural frequency we see. So there may be a pre-stress structures or a spectrum loadings are there. Pre-stress structures means few structures are there which are already being stressed, and then you have to find the natural frequency of it. So the best example I can give and you can imagine is a guitar strings. Okay, so you can see the strings of the guitar which are already been stressed. Okay, so already there is some stress into it, and when some force is being applied and removed, or just wind crosses those strings, what happens? A beautiful sound comes out of it. So and it vibrates, those strings vibrate. So those are, you can find out the natural frequencies of those strings. So it is called as a pre-stress structural analysis, pre-stress modal analysis. Then there would be various harmonic or the frequency response. So there would be many, again, general loading conditions would be there, or pre-stress condition, which you can simulate. Also, there would be a transient dynamics. Okay, whenever the load depends upon the time, we call it as a transient dynamic analysis. So it may be, so this particular transient dynamic condition will include, may include a general loading, or there may be some material or geometric nonlinearities also included into that. So again, there are some thermal problems which can be solvable. So many linear and non-linear steady state and transient heat transfer analysis can be solved. So loading may be a specified temperature or heat flow rate, specified heat flux, internal heat generation rates, convection surfaces or film coefficient, radiation. So the or sometimes the mass transport of heat effects takes place, or temperature dependent material properties are there. So here you can see one example of transient heat transfer of chip. Okay, so this is some electronic device chip is there, and you can find out the transient heat transfer of heat. So again, there are sometimes you come across very difficult problems, right? So like in the structural problems, you may occur with a large deformation or a large strain problems like a forming operation or swagging, extrusion process, or the sometimes you come across soft materials and any problem where the part must be remeshed during the deformation. So such occurrences are related to sometimes explicit dynamics, and those simulations or those problems also can be solved with the simulation. There is explicit solver is also available. So there is Autodyne, LS Dyna, where you can simulate such occurrences. So there would be impact or explosions or implosions are happening. So we have Autodyne solver where you can simulate such occurrence. Then there would be different material behavior like viscoelastic, viscoplastic. So there are various material models available in engineering data sources library of Ansys Workbench, and you can simulate such material behaviors. And also the real life problems won't be just straightforward problems. There would be some coupling like thermoelasticity, or some interactions of electric or magnetic or thermal or abstructural behavior would be happening. So such coupled field analysis can also be solved with the simulation. So there may be some very difficult thermal problems like natural and forced convections, where the pressure and velocity distributions are also not known, or some phase change problems for complex geometry are there. Or so such simulations, we have a transient thermal analysis environment, or sometimes you may have to find out the uh, uh, there would be some problems where you have to include the CFD results also into the thermal problem. You have to do this thermal analysis in CFD, and later you can find out the thermal stresses by importing those temperature results into the structural analysis. So such problems can also be solved with help of Ansys working environment. So just to give you an glimpse that what are all things can be done with ANSYS structural or the finite element method being implemented on ANSYS, you can do, this is a summary of what can be done with the FEA solver available with ANSYS. So you can do strength analysis, which includes linear, nonlinear, static structural transient analysis, steady state and transient thermal analysis. Then in vibrations, you can do modal, harmonic, spectrum, random, and transient analysis. Then durability, you can find out the life of your component, like high cycle fatigue, low cycle fatigue, vibration fatigue you can do. Also, you can work onto the crack propagation and crack growth analysis. Then for rigid body dynamics, we have a tool motion where you can design the rigid mechanisms over here. Then we have Ansys encode, which is which predicts the particular type of components or assemblies. Then you can work on the various additive manufacturing processes. Ansys Autodyne is there for explosions, impacts, and drop testing. You can simulate composite materials. And we have Ansys LS Dyna, where you can work on the various explicit phenomena like crash testing, short impact, or meter crimping. So now I will take the questions first, which you have got. Okay. So what you have to do first, let us start. I hope everyone is opening Ansys Workbench. Great. So now so once you open Ansys Workbench, you can see where sometimes it may be this like this. You have to just click on this plus button, and then you have to select a static structural branch. Okay. So double click on static structural. Okay. Now you just right click on geometry. You click a right mouse button and you import a geometry. Okay, so wherever you have saved this PDF and the geometry file, so you have to import pump assembly. Okay, so just click on that, right click and import the geometry. Okay, this is a pump assembly. Okay, done. Now click on the model phase. Okay, model cell is there. Double click on model. So your Ansys mechanical window where you will be simulating these things will be opening. Meanwhile, we will make some changes into the engineering data. That is, we need to add some information. We need to add some material properties to it. Okay. So double click on engineering data. So can you see this screen now? Everyone able to open the engineering data? Okay. Now in this, you can see filter engineering data, and beside that engineering data sources is there. So you have to click on engineering data sources. In that, double click on general materials. Below that, you can see the library of general materials available here. From it, you have to add polyethylene. Okay. So here number 10, polyethylene is there. From mine is number 10. It may be different number at your end. Beside that, plus sign is there. Okay. So just click on the plus sign. Fine. Come back to your project. You refresh your project so that the added material will be included in your project. Okay. You have to just refresh your project. Now you can check here whether your material is being added here or not. You can see now two materials, structural steel, which is a default material, and you just added the polyethylene material. Okay. Now you have to check on the units. Okay. So whenever you are solving any problem, you have to check on the units. Okay. There are various unit systems available. From that, we have to select this kg Newton metric unit system. Okay. Just click on that. Fine. Now You go back to the geometry. Now you have the first part, that is a pump housing. Okay. Now to this, by default, structural steel is being assigned. Okay. So are you able to follow till this step? So now to pump housing, we have to assign the different material, which is we have taken the polyethylene. So you click on this and below that you can see the assignment, material assignment. You have to just select polyethylene to it. So now you can double check. So for pump housing, I have polyethylene. Then for impeller, the material is structural steel. For pulley, it is structural steel. Then shaft of structural steel. And there is a nut which is again of a structural steel. You can see below. Fine. So now we are done with geometry and assigning material properties to the structure. Okay. Now what we will be doing is we will be now looking at the contacts. Okay. So now you click onto the connections branch and here you can see contacts. So you just click on it. You can see various contact regions. So there is a contact between pump housing. You can just expand to see what contacts are being assigned. So there is a contact, bonded type of contact between pump housing. Yeah.
Sneha, sorry to interrupt. There is a request that you may have to go a little slow, not too slow, because people system are not responding so fast.
Oh, is it? Okay, I will wait. So shall I go back? I don't.
No, I think you can continue, but yeah, when you are doing some operations and the implementation may take a little slow on personal laptops.
Fine, fine, no issues. I will wait now. So you come. I hope I will again see. Go back. So I guess assigning is material property is done. You have to just go to engineering data. You have to click on engineering data sources, then general materials, and from this general material library, you have to just click on this plus sign beside of the polyethylene. Okay. Coming back to project, you have to just refresh your project. So once you refresh your project, open Ansys mechanical branch. It will be open, maybe it will take time. So if you open this geometry cell, you can see total 5 parts are there. So to the pump housing, I have to assign polyethylene material. Okay, so just click on pump housing. Below that, there would be some expansion box will be there. So in their material, you have to assign. If you click on the arrow beside that, you have to just click on polyethylene. So that material property would be applied to the pump housing. Okay, now let's move. So next we have to go to connections. You have to expand the connection tab. Then in that you have to go to contacts. Now you can see there are total 7 contact regions are being detected during this. So by default, software will assign bonded contact to this particular any of the contact region. Okay. Now there is a contact region between the pump housing and the shaft. Okay, that is a third contact region you can see. But there is a tendency of the contact, that is a contact between pump housing and shaft, that it should have some uh, sliding motion between these two. So you have to assign a no separation contact to it. Okay, so you have to select this contact region. You can see contact body is pump housing, target body is shaft. Okay, and then you can see the type of contact. So it by default is assigned bonded, but you have to change it to no separation. Okay, you can see this is no separation contact we have assigned between pump housing and shaft. Okay, you can check another contact regions just to cross check all other contact regions are bonded. Done. I will wait for 1 minute. Okay, now mesh will be automatically generated. Okay, if you are not giving any meshing control, then software will automatically mesh it. Okay, so as of now we are not concentrating on mesh generation. Now come to the static structural branch. Now you highlight this static structural. Okay, you right click onto it. You will be seeing different loads and the boundary condition. Okay, below 4 are acceleration, standard earth gravity, rotational velocity and rotational acceleration. Those could be applied on the complete body. Then you have pressure, force, remote force, bearing load, moment, line pressure. Different types of loads are there which you can apply, and there are various supports. There are then motion loads are there, nodal forces are there, and so on. Okay, so from this you have to select a bearing load. Okay, so those loads are to be applied on a surface. So you can see here only surface is being highlighted. So you just select it and you select the surface on the pulley and just apply. Okay, so you have applied the bearing load on one of the face. Complete this, then I will go ahead. Okay, Are you able to apply the bearing load? You have to select this surface. See, I am just zooming this. You have to select this surface. Okay. Now below that you have to represent it in a some uh, components. So defined by, you can see vector, and beside that the arrow is there. So you just click on that and change it to components. Okay. Now we have to apply 100 Newton of force in x direction. So just enter 100 over here. So 100 Newton of force is being applied, that is bearing force is being applied over here. Okay. Okay. Now go ahead. We have applied now load, that is bearing load we have applied. Now we have to apply the boundary conditions. Okay. So now select this bottom surface. Okay. Right click and insert frictionless support onto it. Okay. So now we have applied frictionless support at the bottom of your pump housing. Okay. Now I have to apply the frictionless support on this all holes of this pump housing. Okay. So please apply the frictionless support at the bottom, because next step you will need to see how I am doing. Done. Now click on to the model cell. Okay, again right click onto the screen. Okay, you just select this one surface, right click, and below that you will be seeing create named selection. Okay, so here you can see there are around 10-11 holes are there. Okay, so to reduce my work, or by selecting every hole, what I am doing, I'm creating a named selection which would be a group of all these holes. Okay, because I need to apply frictionless support on these all holes. Okay, so what I did, I clicked on to the model cell. Okay, then you select this surface. Fine. Click on the model cell. Come here, come to the working space. Click on this surface. Right click, and here you can see create named selection. Below you can see create named selection. Okay. Now you will be seeing this block selection. So I will be selecting the same size holes. Okay. So name selection I am applying to same size of holes in this geometry and OK. Now you can see the name selection is for all the holes in this. So there are total 8 faces which I have selected as a named selection. Okay. You want me to repeat? I will again repeat this. Create a model cell. Go to model cell. Come back to this working space now. Select the surface. Select this face. Right click. Create named selection. Apply geometry atoms of same size. OK. And you will be able to see these 8 surfaces are selected as a named selection. Now come back to static structural, right click, insert, frictionless support. Now in this particular, you have to change the scoping method. Instead of geometry selection, I have to select name selection, and I have already done the name selection. You have from drop down, you have to select that name selection which is named as a selection. Okay. So now you have applied bearing load. Then you have applied frictionless support at the bottom and the frictionless support on this 8 surfaces which we have grouped together as a named selection. Okay. Complete till this point. Now come to the analysis settings. Okay. Now please check these weak springs are off. Okay. So weak springs means if there is some additional, some supports are not assigned properly, or some contacts you have not assigned properly. If if something you have a, that time you put on the weak springs on, so that but the software will automatically assign some support to it. But as of now, you make sure you put off the weak springs effect. Okay. Now come to the solution branch and just solve it. Let your finite element model get solved. Fine. It is been done. I will wait for 1 more minute. Okay. Now what results I want to see? So now you just click on the solution, and here you can see, you go up and see in the solution what are all results you can extract, or just right click and the solution and find out the what are things you want to see. So deformation, I want to know what is the total deformation, so click on to that. I want to know what is the equivalent stress. So since steel is an elastic material, so one misses theories of failure will be applied over here. So I will be selecting the equivalent one misses stress. So just select that, right click and evaluate all the results. So you can see now the total deformation you will be able to see. This is total deformation. You can see on my screen or maybe your screens as well. So it comes about to be 0.079 at my end. The values may be different at your end, okay, how the meshing has happened and all. So for me it is 0.037, but it would be around that only, okay. Some people would have been getting 0.036 or something like that. Let us check on the equivalent stress. So I'm getting 1.15. Okay, so this is the equivalent maximum stress I'm getting. Now, this is for the overall structure or overall assembly you are getting total deformation and total or equivalent strength. Let us say if I want to know the equivalent stress on, let us say, on the impeller. So what I can just, you have to select one body. So go to the body selection. You select this one, this structure, right click, and you can find out total deformation into it. Also for this body you can find out the equivalent stresses and just solve it. Okay, so you would be able to see total deformation into this impeller blades. And so you can see the equivalent stress to it. Fine. I hope you were able to follow the steps.